All right, now covalent bonds. So covalent bonds are actually sharing of electrons. So rather than giving up their electrons or taking electrons, they just put them in the middle and share them. And they can share 2, 4, 6. They do whatever they need to in order to acquire that full octet. And covalent bonds always occur between two nonmetals. Okay, covalent isn't quite as cut and dry as ionic, though. Ionic bonds are flat-out ionic bonds. With covalent, though, you can have nonpolar covalent and you can have polar covalent bonds. And what that distinguishes is the difference in electronegativity. So we talked about effective nuclear charge back when we were talking about periodic trends. If we look at oxygen bonded to hydrogen, so that is a covalent bond, so maybe it appears that they're sharing their electrons, but they're not really sharing fairly. And it's because oxygen, which has a better or a higher effective nuclear charge, will have a stronger pull on those electrons. And so what it means is the electrons are going to spend more time around this oxygen. And so what that creates then is a polar bond. So the electrons are not being shared fairly. It's a polar covalent bond because electrons are being pulled. Ones that are sharing fairly, so they're actually legitimately sharing those two electrons, would be nonpolar. And, this is kind of a spectrum where we go from nonpolar, where they're sharing fairly, to they're not sharing very fairly to the point where one takes from the other. And so we can think of this just as a spectrum from one to the other, where ionic bonds are formed by the highest electronegativity difference. So if we look at the values and subtract them, the strongest electronegativity difference would be an ionic bond. Somewhere in the middle would be polar covalent, and then at the very bottom of the spectrum would be nonpolar. Okay, so you should remember that the periodic trend for electronegativity is that it increases as you go up and over. So the most electronegative element on the periodic table would be fluorine, and the least would be francium. Noble gases don't count. And if we look right here, we have a nonpolar covalent bond, and what the kind of colors here represent is electron density. And so what we see here is that electron density is even throughout this entire thing because those fluorine atoms are sharing those electrons evenly. And they're sharing evenly because it's fluorine versus fluorine. So the electronegativity difference here would be 0, because the electronegativity of fluorine is equal to electronegativity of fluorine. However, when we move over to hydrogen versus fluorine, now if we look on our periodic table, hydrogen is going to have a lower electronegativity than fluorine. So what we see is a darker region here. That means the electrons are spending more time around fluorine, creating a polar covalent bond. And it's polar because fluorine is pulling the electrons away from hydrogen. And if we look up the values for electronegativity, we would find electronegativity of hydrogen is 2.1 and fluorine is 4.0. So if we look at the difference then between these two, 4.0 minus 2.1 would equal 1.9. And so that would be the electronegativity difference between those two. And if we look back at the spectrum from the last page, that would fall within the polar covalent region. And finally, sodium versus fluorine. So fluorine is significantly more electronegative than fluorine, so it doesn't just pull the electrons towards it, it takes the electrons from sodium. And if we look at the negativity values, electronegativity values for those guys, sodium is 0.9 and fluorine is still 4.0. So the difference there would be 3.1, which falls in the ionic spectrum. You can read through this and take notes on this, but I'll kind of give you a summary. What it's saying here is those differences in the sharing of electrons, so the electron density spending more time on one region and not the other, will create what's called a partial negative and positive charge, or dipoles. And we'll look more in depth at dipoles later on when we talk specifically about electronegativity differences. But if we take a look at something like the hydrogen fluoride that we saw in the last slide, so we already said that fluorine is more electronegative than hydrogen, so it means it's going to pull the electrons towards fluorine. So as a result, since there's more electron time around here and less around here, we end up with an imbalance in charges. So as a result, there's going to be a slightly negative charge around fluorine, and we symbolize that with a delta, negative, and a slightly positive around hydrogen, which we symbolize with a delta, positive. And so both of these are called dipoles, or more specifically a dipole moment. And so this would be a positive dipole and a negative dipole around respective elements. Okay, there is a table of electronegativity values inside of your textbook, so if you need to look those up, and you probably will a couple times, find that table and go ahead and mark it in your book so you can come to it easier. So to determine the bond type, we look at that spectrum where it ranges from 0 all the way up to ionic bonds, and we just subtract electronegativities. So hydrogen versus hydrogen, 2.1 minus 2.1 would be a difference of 0. So that tells us that this bond right here is nonpolar covalent, and this molecule would just be H2. All right, here's another example of hydrogen versus carbon. So you can see that there is an electronegativity value difference, 2.1 for hydrogen and 2.5 for carbon, and the difference is 0.4. Now, that's not a lot of difference. So yes, there's going to be a little bit more electron density around carbon, but not much. So overall, this would just be considered a nonpolar covalent because the difference in electronegativities isn't enough to make a difference. Once we get to HBr, though, the difference here is 0.7, and now we are in the polar covalent range. So the difference in electronegativity is here. Bromine is strong enough to pull the electrons towards it and give it a significant enough charge there to make that a delta negative versus a delta positive. So this would be a polar covalent bond. And another example here, you can see the difference is 1.0, so this is polar covalent. We would wind up with a delta negative and a delta positive on those guys. And finally, we see electronegativity difference here of 3 for fluorine versus lithium, and that makes this particular bond ionic.